right, so picking up where we left off, we did an example finding pH, POH, H plus, those kind of things, and we talked about sig fig. So let's do another example. So here in ammonia, it tells us that the hydroxide ion concentration is 4.8 times 10 to the second molar, and it wants us to calculate pH, POH, and H plus. So since we have OH, we can find POH. So remember, POH is the negative log of the hydroxide ion concentration, so the 4.8 times 10 to the negative second. That's going to give us a POH value. And taking into account sig fig, since 4.8 has 2 digits, our POH should have 2 decimal places. So this is going to give us a POH of 1.32. Now we can either find H plus from OH, or we can find pH from POH. There's no right way. There's kind of 2 ways that you can solve here. I tend to like to find pH. So remember, pH plus the POH should be equal to 14. So our pH value when we subtract is going to be equal to 12.68. And then to find H plus, we can either find that using OH negative or pH. I'll solve using pH. So remember, the hydrogen ion concentration is equal to 10 to the negative pH, which is going to give us a concentration of 2.1 times 10 to the 13th. And remember, since our pH has 2 decimals, our concentration needs 2 digits. And remember, concentrations are measured in molarity. So all of those are calculations that we did in Chem 1 as a refresher. All right, so continuing some review from Chem 1, looking at the difference between strong acids and weak acids. And we also covered some of this in Unit 4. So remember, strong acids ionize completely. So they completely separate into ions when dissolved in water. There was the list of strong acids that you guys had to memorize. One of those was hydrochloric acid. So when hydrochloric acid is put in water, it completely ionizes. The hydrogen attaches onto the water to make hydronium, because like we said, we don't have random hydrogens floating around by themselves. And then we have the chloride ions floating around. This is a one single arrow reaction. So remember, it completely produces ions. Whereas weak acids only partially ionize. So remember, a lot of it stays as the original parent acid and produces some of the ions. Remember, these are those equilibrium reactions that we looked at. For strong acids, you can also look at these using particulate diagrams. So we have the hydrochloric acid that we put in water, and notice that there are no hydrochloric acids floating around in that water. We only have the hydroniums and the chlorines, or chloride ions, excuse me. Whereas the weak acid hydrofluoric, there are still some of them floating around in the water, but then we also have some of the hydroniums and some of the fluorides. So with weak acids, you're going to see some of that parent acid still in that solution. So this yet again is just showing before dissociation with strong acids, we only have acid. After dissociation, we only have the ions. Whereas weak acids, we're still going to have a lot of that parent acid and just a little bit of the ions. So with strong acids, whenever we're looking at the hydrogen ion concentration, it is equal to the concentration of the parent acid. Remember, strong acids are considered strong electrolytes because they produce so many ions. They can easily conduct electricity. Where it gets more difficult is with weak acids. Because they do not ionize completely and they are at equilibrium, we need an ice table to calculate our hydrogen ion concentration. We need to look at how much of it ionizes. These are considered weak electrolytes. Sorry, I hit an extra button. So remember, they will conduct electricity, but only a little. And make sure to review your list of strong acids. If it is not on your strong acid list, it is a weak acid and will require an ice table to find the hydrogen ion concentration. So that, yet again, are the ones that are on your memorization list. And anything not on that list is one of your weak acids. And make sure that you double check your acid nomenclature. Sometimes you will be given the formulas, sometimes you will not for some of the things that we can write on our own. All right, so going back to the strong acids and weak acids. With strong acids, there is a weak attraction between the particles, which is why they separate completely. Strong acids have a weak attraction, which is why they ionize completely and break apart so easily. Whereas weak acids, there's a stronger attraction between the particles, so it is harder for them to split apart, which is why they tend to stay together overall and only partially ionize, because it would take a lot of energy to break apart all of that attraction. So we've dealt with strong acids. Those are kind of the easier ones to deal with. So let's look more at weak acids because these tend to give us more trouble. So a weak acid solution is an equilibrium system. It's the acid in water producing the ions, and it is at equilibrium, so it does go back and forth. So weak acid solution contains sorry, I'm missing some of my buttons. So weak acid solution will have mostly non-ionized acid molecules and some of the ions. So looking at hydrochloric acid, which is not on our strong acid list. So at equilibrium, remember, we're always putting the acid in water. So since this is an acid, remember, it loses that hydrogen. So the hydrogen goes over to pair up with the water to make hydronium ions, and then leaves behind the cyanide ions. So we're going to have a lot of reactants here and not a lot of products. So our K value, and notice this is a Ka value because it is measuring the constant for the acid. It is less than 1. It is that decimal number has that negative exponent. So that's a clue that this is a weak acid. So looking at what the Ka actually tells us. So very similar to all of our other K values in KSP, Ka is going to tell us the relative strength of the acid or the amount of ionization. And just like our other K values, we're looking to see what is closest to 1. So for weak acids, they're all going to be less than 1, but the closer to 1, the stronger the acid. So here you're given the Ka values for nitrous acid, acetic acid, and hydrocyanic acid. Notice that the Ka for nitrous acid has the smaller exponent. That is the larger value. That is the strongest of these three acids. Now looking at bases, same kind of things apply. There are strong and weak bases are used in the same way to describe bases. So strong bases completely dissociate or ionize. Weak bases only slightly dissociate or ionize. And yet again, go back to your memorization list for your strong bases. The calcium hydroxide that is marked as borderline, it acts strong at low concentrations, but higher concentrations, it does not ionize completely. You should not have one of those that you have to deal with. So looking at the particulate level, a strong base, like we said, when it goes in water, completely ionizes. So sodium hydroxide is one of those that is on your list. Whenever it goes in water, we only have the sodium ions and the hydroxide ions. We don't have any of the sodium hydroxide left floating around in water. Whereas ammonia is a weak base. When it goes in water, we still have some of the ammonia, but then we also have the ammonium floating around and hydroxide. So we have the ions with its parent base. So our most common weak base we deal with is ammonia. And then a lot of other weak bases are some sort of derivative of ammonia. So a lot of times one of the hydrogens is replaced with another organic group, but it'll still have that NH in there. You're not going to have to recognize these unless it specifically asks you to figure out, like, is this an acid or is this a base from a reaction? So here you can see they have a similar structure in that electron pair that can kind of bond and attach with a hydrogen. So another thing from Chem 1 that you talked about was the difference between concentrate and dilute, as well as strong and weak. Remember, these two terms are not synonymous with one another. They are describing two different things. So between concentrate and dilute, concentrated means it has a high molarity. There's a lot dissolved in that given volume, whereas dilute refers to a lower molarity. So there's not a lot of particles in that given volume. So we tend to look at molarity when determining if something is concentrated or dilute. Whereas whenever we're comparing strong and weak, we're looking at the amount of ionization. So strong acids and bases ionize completely. Weak acids and bases only ionize slightly. So if we want to look at this, here is depicted a concentrated solution. There are a lot of ions in that given space. And this is depicting a strong acid because all of them are dissociated. Whereas here, we still have a strong acid. We only have ions, but this is a dilute solution. There are not a lot of particles in that same given space. We can also look at this in terms of the weak acid. So here in the top right is a concentrated solution. There are a lot of particles in that given space, but notice the red HAs. Those are our parent acids. It's a hydrogen with some anion. There are a lot of the parent acid and not a lot of ions. And same thing, we can have a dilute solution of that weak acid with not a lot of particles dissolved, but we still have a lot of that parent acid, not many of them ionized. And remember, what makes a solution acidic is that it produces those hydrogens in water, so hydrogen or hydronium. All right, so let's actually get to, like I said, the weak acids. We have to use an ice table to figure out the actual pH of them, because not all of it ionizes, so the concentration of the acid is not the same as the concentration of the hydrogen ion concentration. So here we have lactic acid, which anything which is not a common acid or not one of your polyatomics that you had to know, you will be given the formula. Or you can solve it without the formula. But lactic acid, which is HC3H5O3, which is present in sour milk, also gives sauerkraut its tartness. So it has that sour flavor for us. It is considered a monoprotic acid. So remember, that's whenever it only has one hydrogen that ionizes, that one in the front. It tells us in a 0.1 molar solution of lactic acid, the pH is 2.44 at 25 degrees Celsius. Wants us to calculate Ka for lactic acid. So remember, weak acids are an equilibrium system. So here we have HC3H5O3. Remember, we always put acids in water, so you're always going to have water as one of your reactants. And that, the acid is going to give up a hydrogen, so produce lactate, which is C3H5O3, and the hydronium ion. And remember, all of these are aqueous except water is a liquid, so we kind of ignore water for our ice table. So here it tells us that we start off with 1 molar lactic acid. If we're starting off with that acid, we have none of the parent of the ions initially. The only other information we have here, because it didn't give us the change amount or the equilibrium amount, but it did give us the pH. So if we have the pH, we can find H+, which is the same thing as hydronium. So remember, that's 10 to the negative pH. So our hydrogen ion concentration is going to be 0.0036. So that is how much hydrogen is produced, which is our equilibrium amount. So now that we know one of the equilibrium amounts, we can kind of fill in all the blanks. That means that we added the 0.0036 on the reactant side, or excuse me, on the product side. Means we need to subtract that much on the reactant side. So at equilibrium, we have 0.0964 molar lactic acid, 0.0036 molar lactate ion, and hydronium ion. So to solve for Ka, which it wants, this is still the same version of K, where we have the products on top divided by the reactants on the bottom. So our products on top, we have the lactate, which is the 0.0036. We have the hydronium, which is 0.0036. And then we have the lactic acid on the bottom, the 0.0964. And we figure out that our Ka value is equal to 1.3 times 10 to the negative fourth. So that is an ice table dealing with a weak acid. The same kind of stuff we dealt with in our equilibrium unit. But it's yet again figuring out, it may want you to find pH at the end of this. It may give you the pH to tell you how much it ionizes. There's going to be different clues that we can look for when solving. So let's look at another problem. Here it says a student planned an experiment that would use 0.1 molar propionic acid, which is HC3H5O2. It wants us to calculate the values of the hydrogen ion concentration and pH for the solution. And it tells us propionic acid has a Ka value of 1.4 times 10 to the negative fifth. So this is a sample like we did in equilibrium where we do not have any of our equilibrium values. So we need to write our formula first. We have the HC3H5O2. We add that to water, and that's at equilibrium, producing the hydronium ion concentration and the propionate, which is C3H5O2 negative. So it told us that we started off with 0.10 molar propionic acid. Remember, we kind of ignore water. And we don't start off with any of our original ions. We know that since we have none of the ions at the beginning, we have to increase by a factor of X on our product side. And we need to decrease by a factor of X on our reactant side. So using that, we can plug into Ka to figure out the value of X. So we have our products on top, so we have X times X. You can also rewrite that as X squared. This, we can ignore X here because the 0.10 would be to the negative first, and our K is to the negative fifth. That will make your math a little bit easier. And we said that is equal to 1.4 times 10 to the negative fifth. So we can multiply by the 0.1, and I'm going to simplify this as X squared is equal to, sorry, I did not write that number down. So we would need to multiply the 1.4 times 10 to the negative fifth times 0.10, and then take the square root of that to figure out that X is equal to 0.0012 molar, which is our hydrogen ion concentration, because that is just going to plug right back in. The other part of this is it wanted us to find pH. Remember, pH is our negative log of that hydrogen ion concentration. So when we plug that in, we get that this has a pH of 2.93. So yet again, that's just another thing it may want you to find, is if it gives you the Ka, finding that concentration in pH, or it may give you that concentration so that you have an equilibrium value. All right, and same kind of thing can occur with bases. So weak bases, you'll also need an ice table for. But it works the exact same way as those weak acids. So it says here we have a solution of hydrazine, which is C2H4, has a concentration of 0.25 molar, and it wants to know the pH of the solution. Now, it did not tell you this was a base. However, it tells you the Kb value. So Kb is for bases, Ka is for acids. So the Kb of hydrazine is 1.7 times 10 to the negative 6. So because it gave us a Kb value, we know this is a base. So we can still write out a reaction. So C2H4, bases also go in water. But remember that bases gain a hydrogen. So this will end up being C2H5 plus, and then hydroxide is what's left over in that water. You could have written the hydrogen in front of the C2H4 or just included it. Either way is fine. So clues that it gives us is it tells us the hydrazine has a concentration of 0.25 molar. Remember, we're going to ignore water, and we didn't start with any of the ions. And it gives us Kb, so we don't have any of our equilibrium values. So just like the last problem, that means that we increase by a factor of X on the product side because we cannot subtract from 0. We decrease by a factor of X on the reactant side. And we can plug those into our Kb equation, which yet again is the same products over reactants. So we have our C2H5 plus, which is going to be X. Our hydroxide is going to be X. Divided by, we can ignore the X factor for the hydrazine, so it's just going to be 0.25. And we said our Kb was 1.7 times 10 to the negative 6. So multiply by the 0.25 and then take the square root. And we get that X is equal to 6.5 times 10 to the negative 4th molar. Now that is our hydroxide ion concentration. So we cannot find pH from hydroxide. However, we can find POH by doing the negative log of the hydroxide, the 6.5 times 10 to the negative 4th. So we have a POH value equal to 3.19. So then remember pH is going to be the 14 minus the 3.19. So our pH is equal to 10.81. That's a common mistake, is people will take the X and tell me that the pH is 3.14, or excuse me, 19, but you cannot find pH from hydroxide. So you have to find either H plus to then change into pH, or you have to find POH to then change into pH. So with the Ka and Kb of our weak acids and weak bases, we can also bring this back to our conjugate acid base pairs. So the Kw that was the hydrogen hydroxide was equal to the 1.0 times 10 to the negative 4th. For conjugate acid base pairs, if we take the Ka of the weak acid and the Kb of its conjugate base, multiply those together, it also equals that ion product constant for water, the 1.0 times 10 to the negative 14. So sometimes in our textbook, we might have a table of Ka, but we need a Kb value. We can figure that out overall. So a conjugate acid base pair, remember, only differs by one hydrogen. So here we have ammonia and ammonium. But since ammonia is a weak base, you may only have a Kb value. But if we need to find the Ka value, we simply plug it in, and we will do the 1.0 times 10 to the negative 14th divided by the Kb value to find a Ka value, which would end up being 5.6 times 10 to the negative 10th. And you'll notice that the higher value, the 1.8 times 10 to the negative 5th, is Kb. So we know that this is a weak base overall. So same kind of deal here. I just pulled a couple other ones for you to look at. Here we have nitrous acid and the nitrate ion. Nitrous acid has a Ka value of 4.0 times 10 to the negative 4th. And the nitrate or nitrite ion, excuse me, has a Kb value of 2.5 times 10 to the negative 11th. The other one, the HOCl and OCl negative, notice that the Ka value is 3.5 times 10 to the negative 8. the Kb value would be 2.9 times 10 to the negative 7th. So this would be a more basic solution because the Kb is the higher of the two values, whereas nitrous acid is more acidic because Ka was the higher value. So in general, the stronger a Bronsted acid is, the weaker its conjugate base. So notice that the Kb value for nitrous acid was lower. And on the flip side, the stronger Bronsted base, the weaker its conjugate acid. We are going to come back to this in our next section when we start adding in and talking about salts.